So let's take first point, that is condition for light emission. Right. So condition for light emission is, of course, we all know that whenever one electron that recombines with a hole, then this recombination may generate a photon. However, this is not very simple, because if we see the band structure of a material, so this is a kind of uh, particle interaction. There are a lot of particles inside a lattice. Okay, so some of them are electrons. Of course, electrons means free electrons, electrons in conduction band. Holes, of course, means vacant places in the valence band. If you see a silicon structure, even though I should not take a single silicon structure right now, but anyway, to understand, we can have it. So these are all silicon atoms, right? The electrons contributing into this covalent bond, they are called the valence electrons, and one electron which is free of all these bondings, they are free to move inside the lattice, that is called the conduction electron. Okay, and if there are some vacancy in the covalent bond, that means this is called vacant state or holes. That's why they are represented in valence band. Vacancies in valence band. Apart from that, these lattices are actually vibrating with some frequency and amplitude. All of these depending on the temperature. So these are called phonons. Generally, phonons have very high momentum, but low, very high momentum, but low energy. Energy is generally of the order of some milli electron volts, and delta K can be quite large for phonons. Apart from these phonons, photons have characteristic like delta K, that is the momentum, that is very small, approximately equal to 0, and delta E, that is the energy of a photon, that is h nu, that is quite high. So these are of the order of electron volts. Now, when one electron recombines with a hole, that light, that energy will be emitted as a photon or as a phonon. That depends on this energy and momentum conservation. If the electron which is actually falling, and if it can find the holes at same momentum space, of course, for this transition we don't need any, delta K is approximately equal to 0. So in this case, this transition will emit a photon. However, if you see the band structure of silicon, which is unfortunately like this. So it's minimum of the valence band, minimum of the conduction band, and maximum of valence band, they don't lie on the same momentum vector K. And that is why it involves a finite momentum. So the probability that this electron will recombine with a hole emission of h nu is very less probable. It is not like that it is impossible, but very less probable. Okay, then how this energy goes? This energy goes into lattice vibration, so in terms of phonons. Okay, so the first condition for light emission is that the material should be direct band gap material. Direct band gap semiconductor. Okay, so this is one condition. Another condition is that even if some electrons or photons is being emitted, this emitted photon, there is a very high chance that it will again excite. This will be absorbed by the material because this emitted photons is still inside the semiconductor. So there is a very high chance that this will get absorbed in the material. Okay, so again it will create one electron hole pair. Okay, so it will be absorbed and it will create a one electron hole pair once again, right? So sufficient number of electron hole recombination. So these are two conditions for light emission from a semiconductor. LED actually that provides all these two conditions. First of all is that if a PN junction made of direct band gap material, let's assume gallium arsenide. Okay, and if it has P and N type, and if you are making it a little forward bias, if you see in terms of energy, what will happen? At normal position, when there is no forward bias, the band structure will look like this. And this is the junction area, let's say. So the electrons will be probably up to this line. So here you have lot of holes. Here you have plenty of electrons. However, they are separated. Okay, they are separated. There is plenty of holes in p side. There are plenty of electrons in n side, but they are separated right now. In a common area, no very high density of electron or holes are available. However, when you do a little forward bias, the structure will look like this. So in this case, you will have sufficient number of electrons in this region, not very high as compared to this side. This side will be having a lot of electrons. However, because you have forward bias, so some of these electrons that will be diffusing in this region. Okay, so in the junction region, you will find sufficient amount of delta N and sufficient amount of delta P because of hole injection from P side to this junction region. Now, what will happen is that these electrons and holes will recombine and they will emit photons h nu that will be equal to Eg, n is equal to 1.24 divided by lambda in micrometer. The answer will be in electron volts. Okay, this is how uh, this is a basic principle of an LED. So whenever you do a little forward bias, what will happen is that a lot of electrons will come in this region and lot of holes will come in this junction region, and in this junction region especially the electron hole recombination that will happen and light will be emitted from this junction. If you see in the as a structure, it will look like this. Okay, so this is the P region, this is N region. So in the junction region a lot of, okay, so you are giving negative to this terminal and positive to this terminal. So holes are being diffused in the junction region. Likewise, electron is being diffused from this side. So they will recombine and they will give you one photon. So at the edge, it will be emitted. Now this emitted photons, actually it is not that it is this photon will go in only in one direction. It will be actually emitted in all directions. Okay. So very small fraction of the emitted photons that will actually go, we can collect from this side. So very small angle that you will collect. So the emitted light, you can say. So I will come to this point later on. So this topic I have covered, that what is the conditions for light emission. The second topic is LED characteristics. To understand LED characteristic, especially the spectral characteristic. So I want to know that what will be the different frequencies of this emitted light. To understand that, if the material has a band gap of Eg, then of course we know that the electron and hole concentration will be something like this. Right? So this is electron concentration, this is hole concentration profile, and the possible recombinations emitted light frequencies that may vary from here to here, right? So if you go for very large energy, or in terms of lambda, if you go for very small wavelengths, of course the emission will be zero, and it will go maximum up to the band gap, that is lambda c is equal to 1.24 divided by Eg. So here, of course, after this it will be 0. So generally the characteristics are like this, and this wavelength delta lambda, that varies around 80 to 90 nanometers. Okay, so if you see this, because and the maxima will be slightly less than, you see, so you can say that this is lambda max, that corresponds to this energy, which is slightly more than band gap energy, and hence it will, the lambda will be slightly less than lambda c. Now these emissions are spontaneous emission, and generally the delta lambda, that is 80 to 90 nanometer. These LEDs can be used as a lighting, but they cannot be used. Okay, so these LEDs cannot be used as a light source in optical communication. In very early days people were using it because there was not there was no concept of WDM systems like that. Only one channel was there in a multimodal fiber. Okay, and that's why earlier these LEDs was even used. But nowadays we have especially called laser diodes. So these laser diodes, they are not having only P and N type, but it has a number of different layers just for refining this structure. So actually for that application we want that all these powers that should be centered around some particular wavelength, and this delta lambda that should be less than zero point 0.1 or 0.2 nanometer. The next point is output power characteristic. Now, if you want to understand, let's assume the diode current is ID. That will be, of course, it is because it is a diode, so it will be having ID of the equation like e to the power Vt upon Vt minus 1 beta Vt, let's say, was normal diode equation, and it will be having current voltage relation like this. However, generally this cutoff is actually quite a little larger as compared to normal silicon diodes. Now, if the current is ID, the total number of charges you can find delta n is equal to I upon E, you can say. So this is the change in electron or hole concentrations. So per second. So these are the number of electrons or holes recombining per second that you can identify. Now, depending on the recombination time, so some of them might be having a radiative recombination, some of them might be having non-radiative recombination. So it is not that even in LEDs all 100% are actually forming radiative recombination, because for non-radiative recombination also the possibilities are there. So the overall time constant that can be written as 1 upon tau r, r radiative recombination, plus 1 by tau nr, and we define internal quantum efficiency as tau upon tau radiative recombination. This is called internal quantum efficiency, and this gives you one idea that percent of carriers recombining as radiative recombination, right? So if this is given, now you can say that the power generated, that will be equal to eta internal. So what is the fraction of that? Then I upon E. So this was total delta n. So this was your total number of carriers. Out of that, how many of them are actually giving radiative recombination, multiplied by energy of one photon, because this is per second, this factor is delta n per second, so this will give you power. You can see that P generated is proportional to I, that is important. Okay, and also generally we write P out is equal to eta external into I upon E into HD. So there is a difference. Generally, eta external is smaller than eta internal because some of the radiated light that might be again that will be consumed, and that's why if eta internal approximately, let's say it is 0.9, then eta external will be approximately equal to 0.8 or 0.7, something like that. Okay, or 0.6. So even some of these generated photons, they are being consumed inside the semiconductor, and that's why eta external is always less than eta internal. Okay, if we talk about the power profile, P out as a function of input current, LED current ID, so it should be linear. However, this linear relationship doesn't actually holds for a very high current ID that actually saturates after some time. So generally this is like this curve. This is the output power or the light power as a function of current ID. This region is called the saturation region, and this saturation is because of the I square R losses. Okay, because at a small current, this I square R, that is the heating loss, that is very small in LEDs for a small current, and P on is directly all the power, all the energy is going as a light, is being emitted as light. However, when current is quite large, this will dominate, and that's why the output light power that will saturate. So we have covered the second point also. Now let me explain the LED structure. Generally, LEDs are not a very simple one layer, but generally we have a number of layers. Okay, so this P plus gallium nitride layer, that is basically used for ohmic contact over here. Then these three layers, one, uh, two, and this one, three. So these three layers are actually more important. This P layer that supplies holes in this multiple quantum wells. I will come to that why we have this structure. And this N type aluminum gallium nitride. So that will work as, so they have written this code. This is aluminum gallium nitride. Okay, same material. And this multi quantum well that could be indium gallium nitride. So if you see this structure, let's say plot this as a X from here, then you will find that the structure is like this. This is aluminum gallium nitride. Of course, this is P type, this is N type, and in between we have indium gallium nitride. Indium gallium nitride has a band gap which is smaller than aluminum gallium nitride. So the structure will look like this. Okay, generally this is of the order of 4 electron volts, and this one is approximately 3 electron volts. Now if this multiple quantum well structure, if that is very thin, if the thickness of this layer is very small, then the energy levels will not be continuous but discrete energy levels. And that's why if you give a little small forward bias, the structure will become like this. It will look like this. Okay, so on this side you have algan, and this area is indium gallium nitride. So all these electrons from the n side that will actually come to this quantum well region, and they will occupy very high density of electrons being occupied this energy state. Likewise, all the holes in the p type aluminum gallium nitride that will move to this region and they will occupy this energy state, and all the recombination will happen in this active region. So this is called active region. So this region is called active region. Okay. So this is active region or active area where actually the light emissions are taking place. So from this side holes are being injected, from this side electrons are being injected, all are coming in the active region, and this is designed especially in a way that high electron and hole concentration that can exist in the same region, and recombination will start, and this will give you light which will be most probably most of the constituent that will be corresponding to this. Let's say it is E1, so you will get as a lambda very high peak at this lambda 1 is equal to 1.24 divided by E1. Of course, it will have smaller electron concentration on the other energy states also, but that will be a little very small. So let's say it is lambda 2, and lambda 2 is equal to 1.24 divided by E2, where this energy from here to here, that is your E2. So in this way you can see that a very high dominant line you can find at lambda 1 corresponding to this energy level. Unlikely earlier, when actually normal LEDs we were having this very broad spontaneous emission, and the line width was around 80 nanometer. Here this line will be of the order of 1 nanometer or even less than 1 nanometer. Okay, and also we have the electrodes, they are actually quite below this active layer so that emissions can take place. So this is a kind of the edge emitting diode, light emitting diode LED. Okay. Likewise, there is also surface emitting diodes also, in which actually the coupling of optical fibers are very easy. Okay, so generally the lights are being uh, extracted from the surface. So anyway, don't go into that much detail. This topic I think I have covered. Now the materials for LED, how to decide that which material I should use. So you can use any one of these materials with the firm line. Firm line in this graph, it is showing direct band gap material. Direct band gap material. And this is called indirect band gap material with the dotted lines. Here you can see that whatever color you want for LED, accordingly you can decide your materials. For example, the gallium arsenide working as a substrate, if you dope gallium arsenide with some aluminum, okay, into it. So that will give you aluminum, that gallium will be replaced a little bit, okay, with the same mole fraction and arsenide. So this line is giving you aluminum gallium arsenide. Of course, so that will depend, okay, how much fraction you are having of aluminum. Accordingly, the band gap will change for the same lattice constant. Okay, so lattice constant is important because we don't want, okay, so lattice constant mismatch less than 5% or even 2% is allowed for good uh, integration, okay, defect free integration. So the substrate is actually gallium arsenide. On that you are having a different material layer, that is aluminum gallium arsenide. So to reduce the defect levels, it is very important that the new material should have lattice constant mismatch less than 2%. So that is very much applicable over here because they are almost like having the same lattice constant. However, you can also use gallium nitride as a substrate, and this line is showing you indium gallium nitride. Okay, because on this line you are moving towards indium nitride. So if you have a gallium nitride substrate and if you dope indium, you will get indium X, uh, gallium 1 minus X, and nitride. So this material you can have. Of course, with doping, because the band gap changes, and hence you should find the correct molar fraction for your application. One more thing is important over here, that is called uh, so I have talked about the electrical confinement, how the carriers are being confined in this region. There is also a term that is called optical confinement. Optical confinement is uh, is also happening over here, and that is because of the fact that if Eg is high, this implies that refractive index is low. So this is refractive index, okay. Beta is I should write it with okay. So the refractive index is low. As you can see that the air which has very high band gap, refractive index is close to 1. Glass that has also has high band gap but not as of air, so its refractive index is a little higher. So as you decrease the band gap, the refractive index increases, or if the band gap is more, refractive index is low. This is a common identification, common relation, okay. Most of the time it is true for materials, and that's why this has a lower refractive index, and this region indium gallium nitride, that will be having eta uh, 2, which will be greater than this. Let's say it is eta 1, and that's why any light generated in this area, that will go to a total internal reflection, okay. So if this region eta 2, which is greater than eta 1, let's assume this material is all are eta 1, any light generated in this region, okay, so after some time it will get total internal reflection. However, if some light is actually going very normal to the surface, of course they will actually go to the other side, but in general most of the light they will actually follow the total internal reflection. So all the optical light, emitted light, that will be confined in this region only, and that's why the output of the light from this region, that will be quite high. Okay, they will not leak to the other side. Okay, so these are not allowed. The probability that it will move in this layer only, that is quite high, and ultimately you will get a output like this. Okay, of course there the output will not be exactly circular, it will be a little elliptical, because this layer, that is very, it is like this. Okay, so these areas are like this, very thin aperture, and this thickness is generally few nanometer. So the output from this layer, that will diverge more in this direction, because the aperture is very small, so there will be diffraction. Okay, so diffraction will be more in the vertical direction as compared to horizontal direction. So it will have vertical direction like this, and horizontal direction very small. So the overall, the profile will be elliptical. Okay, so I think I have covered this topic in quite detail. If you have any questions, you can ask me. Okay.